Today, we're tackling something truly fundamental, the order of operations.
Ah, PEMDAS, or maybe
Yeah.
BODMS, depending on where you learned it.
Right, think of it like the secret code, the grammar for arithmetic. It's absolutely key. We're drawing a lot from Dr. Michel Enrique Gamboa Graus's Mathematics Review Guide. It's a guide Mr. Gamboa, put together for students in the British Virgin Islands. But honestly, it gives a really clear perspective on rules we sometimes take for granted. We've sifted through a good amount of material to figure out not just what the rules are, but really why they matter so much.
And it's not just about getting the right answer on a math test, is it?
Not at all. It's for everything calculating your grocery bill, programming computers.
It's about shared understanding. Imagine if we all interpreted the same math problem differently.
Chaos.
Complete chaos.
So our goal today is to make sure you understand why we solve problems this way, the same way mathematicians do it globally, so you can feel confident tackling numbers.
Okay, so let's jump right in. What actually happens if we don't follow the rules? Let's use a really clear example. How about 10 plus 5 up 2?
Perfect. Simple looking, but potentially tricky. Yeah, so if you just read it left to right, like a sentence, you might do 10 plus 5 first. That gives you 15.
Yeah.
And then 15 times 2, that's 30. Seems straightforward enough.
It seems that way, but that's not how the agreed upon rules work, is it?
No. What's the correct way?
Well, the standard order says multiplication comes before addition, so you have to do the 5 times 2 first.
Okay, 5 times 2 is 10.
Right. Then you add the initial 10, so it's 10.10.
Which is 20.
Exactly. 20.
Wow. So same problem. 10 plus 5 on 2 gives us 20 or 30, depending only on the order we do it in. That's a huge difference.
It really is. And it perfectly illustrates why we need a standard. PEMDAS, or BODMAS, provides that standard. Parentheses, exponents, multiplication, division, addition, subtraction.
And you mentioned something fascinating earlier, that these rules aren't like, say, the law of gravity. They're a convention.
That's right. It's a human agreement. Think of it like grammar in language. We needed agreed-upon rules so mathematical expressions wouldn't be ambiguous. Before things solidified, maybe back in the 16th, 17th centuries, different people did get different answers.
Which must have slowed things down. Science engineering.
Immensely. So this universal standard evolved. It's essential for communication, for everything from, basic accounting to launching spacecraft. It truly is the grammar of math.
I like that, the grammar of math. Okay, so let's unpack this grammar guide, this PEMDAS, a bit more.
Let's do it. It's basically a hierarchy.
Right, so P comes first, parentheses, or brackets sometimes.
Exactly. Anything inside or needs to be done absolutely first. They're like a VIP section. They override the normal order within those symbols.
Or sign saying, deal with this bit first.
Precisely. It removes ambiguity. You can force a certain calculation to happen first by putting it in parentheses.
Okay, P for parentheses. Got it. What's next?
E is for exponents. That means powers, like 2 squared, or roots, like the square root of 9. Those come after parentheses, but before the next steps.
Powers and roots. Check.
Then we get to MD, multiplication and division.
And this is a really key point, isn't it? They have equal priority.
Exactly equal. This trips people up sometimes. You don't always do multiplication before division. You do them as they appear, reading from left to right.
So if division comes first in the problem, you do that first.
Yes. If it's, say, 10A2, okay, 5, you do 10A2 equals 5 first, then 5I5 equals 25. Left to right for operations on the same level.
Okay, that left to right rule is critical for MD.
And it's the exact same principle for the last pair. AS, addition and subtraction.
Also equal priority.
Also equal priority. Once you've done all the P, E, M, and D, you handle all the A and S, again, just working straight across from left to right.
So not always addition before subtraction.
Nope. Whichever one you encounter first as you move left.
Okay, so let's summarize that flow. Start. Handle anything in parentheses. Then exponents. Then multiplication and division, strictly left to right. Then addition and subtraction, also strictly left to right. Finish.
That's the map. Follow that and you'll navigate correctly every time.
All right, theory is great, but let's put it into practice. This is where it really clicks, I think. Let's walk through one together. How about this? 50, 15A3 plus 8A2.
Good one. It's got a few different operations in there. So looking at 15A3 plus 8A2, what's screaming do me first based on PEMDAS?
Definitely the parentheses, that 15A3 part.
Right. And what's 15 divided by 3?
That's 5. So our problem now simplifies down to 55 plus 8A2.
Perfect. Parentheses handled. What's next in the hierarchy? Any exponents?
No exponents in this one. So we move to multiplication and division, left to right.
Okay, scan the expression. 55 plus 882. What do you see?
I see the 882 at the end there.
Exactly. So we need to calculate that next.
8 times 2 is 16. So now we have 55 plus 16.
Excellent. See how we didn't just go left to right initially? We jumped to the multiplication because it has higher priority than the subtraction or addition flanking it.
Right. Okay, so 55 plus 16. Now what?
Now we're down to the last level, addition and subtraction. And what's the rule here?
Equal priority, so work from left to right.
Yep.
The first thing is 55.
Which is?
45. So we're left with just 45 plus 16.
And the final step?
45 plus 16.
And that's 61.
Final answer, 61.
Nicely done. See how following the steps systematically just leads you straight to the one correct answer? No ambiguity.
It really does provide clarity. Okay, let's shift gears slightly. Time for a little brain teaser we found in the source materials. Ready?
Steer.
I am a number. If you add 15 to me, then multiply the result by 2, you get 50. What number am I? There's a hint, too. Try working backward.
Ah, I like these. Reverse engineering the math. Okay, so we end up at 50.
Right.
The last thing done was multiply the result by 2. So to undo that, we do the opposite. Divide by 2.
Okay, 50 divided by 2 is 25.
Right. Now, the step before multiplying by 2 was add 15 to me. So we undo that. The opposite of adding 15 is?
Subtracting 15, so 25 minus 15.
Which gives us 10. So the mystery number should be 10?
Let's check it. If the number is 10, add 15, that's 25. Multiply the result by 2. 25 times 2 is 50. It works.
Perfect. That working backward logic is super useful in lots of problem solving, not just math riddles.
Absolutely. And that leads us perfectly into thinking about mathematics in action.
Yeah.
How does PEMDAS show up in just regular life?
Oh, all the time. Often without us even explicitly thinking PEMDAS. Let's take a couple of real-world examples.
Okay.
Scenario 1. A sailing team, 8 members. They win $600.
Nice.
But first, they spend $120 on a celebration dinner. Then they split the rest equally. How much does each person get?
Okay, so first they spend, then they divide. The spending has to happen before the splitting of the remainder.
Exactly. So the expression would naturally use parentheses to show that. 600, 120.8.
Right. The parentheses make sure we subtract first. 600 minus 120 is 480.
Uh-huh. And then 480 divided by the 8 team members.
That's $60 each. Makes sense. If you did 600 divided by 8 first, you'd get a totally wrong number.
Totally wrong.
No.
See? Parentheses reflect the real-world sequence. Okay, another one. You're buying souvenirs. Let's say 2 T-shirts at $15 each, plus 3 keychains at $5 each, and maybe 1 hat for $20. What's the total cost?
Okay, multiple items, different quantities and prices. How would we write that out?
You'd calculate the cost for each type of item first, then add them up. So maybe 2I15 for the shirts, plus 3I5 for the keychains, plus the 20 for the hat.
So 2I15 plus 3I5 plus 20.
Right. And PEMDAS tells us to do the multiplications inside the parentheses first, or just the multiplications first, even without parentheses here, because M comes before A.
Okay, 2 times 15 is 30, and 3 times 5 is 15. So the expression becomes 30 plus 15 plus 20.
Yep. And now just add left to right.
30 plus 15 is 45, plus 20 is 65. So $65 total.
Exactly. It seems simple, but following that structure prevents errors when things get more complicated. It helps you organize the calculation logically.
It really does.
The guide also had that beach BBQ problem, which had 2 parts. Kind of reflects how real situations often have multiple questions tied together.
Yeah, that's a good one. Part A was about burgers versus buns. 3 boxes of 12 burgers and 2 packs of 8 buns. How many more burgers than buns?
Okay, burgers. 3I12, buns. 2E8. We need the difference, so calculate each total, then subtract. 3I12, 2E.
Right. 3A12 is 36 burgers. 2E8 is 16 buns.
So 36, 16, 20. There are 20 more burgers than buns. Might need more buns.
Huh, probably. Good planning insight right there.
Yeah.
And part B was simple. Buying 4 cooler bags at $5 each.
Easy one. 4 or 5, that's $20 for the bags.
Right. Breaking down bigger scenarios into these smaller, manageable chunks, each following PEMDAS, is a really practical skill. It makes tackling even slightly complex real-world money stuff feel much more manageable. Okay, let's push this a bit further with our project challenge. We're calling it Fundraising Festival Fun.
All right, let's have some fun.
So imagine a school festival. Big success. They sold 200 tickets before the event at $10 each. Then on the day, they sold another 150 tickets, also for $10 each. Their total costs for things like decorations and prizes came out to $500. The question is, what was their final profit?
Okay, profit. That means total money in minus total money out.
Right. So how would you set up the calculation? Maybe take a second, listeners, to think about the expression.
There are a couple of equally good ways. You could calculate the pre-sale money, then the day of money, add those, then subtract costs, like 208.10 plus 158.10, 500.
Okay, so 2,000 plus 1,500, 500.
Yeah.
That's 3,500, 500, which is $3,000 profit.
Exactly. Or you could realize all tickets were $10. So you could find the total number of tickets first. 200 plus 150 equals 350 tickets, then multiply by the price. 350.10 equals $3,500 revenue, then subtract costs. 3,500, 500 equals $3,000 profit.
Using the distributive property in reverse, essentially. 200 plus 150, 10, 500. Same result.
Same result. PEMDAS handles both correctly. Now, for the really interesting part, the what-ifs. This is where understanding the structure really pays off for planning.
Okay, what if, number one,
What if those tickets sold on the day weren't $10, but were actually $12 each? Maybe a last-minute price bump. Pre-sales were still $200 at $10, cost still $500. How does that change the profit?
Okay, so the first part is the same. 200 times 10 is $2,000. But the second part changes. It's now 150 tickets times $12. Let's see, 150 times 10 is 1,500 plus 150 times 2 is 300. So that's $1,800 for the day of tickets.
Right, so the new expression is 200 day 10 plus 150 at 12, 500, or 2,000 plus 1,800, 500.
2,000 plus 1,800 is 3,800 minus 500. That's $3,300 profit.
$3,300. So that $2 price increase on day of tickets netted them an extra $300. Useful to know for next year's planning, right?
Definitely. Okay, one more what if. This one needs that backward thinking again.
Let's do it.
What if the school had a specific goal? Make exactly $3,500 in profit. Costs are still $500. Pre-sale tickets are still $200 sold at $10. How many tickets would they need to have sold on the day, assuming those day of tickets are $10 each, to hit that $3,500 target?
Okay, working backward from the target profit. We want $3,500 profit. We know costs are $500, so what's the total revenue they needed to bring in?
Revenue would have to cover costs and the profit. So $3,500 plus $500 costs equals $4,000 total revenue needed.
Perfect. Step one done. Now, how much revenue do they already secure from pre-sales?
That was 200 tickets at $10 each. So $2,000 from pre-sales.
Right. So if they need $4,000 total revenue, and they already have $2,000, how much more revenue do they need to generate from the day of sales?
$4,000 needed minus $2,000 already got. $2,000 still needed.
Exactly. And if those day of tickets sell for $10 each, how many do they need to sell to make that $2,000?
$2,000 needed divided by $10 per ticket. That's 200 tickets. They needed to sell 200 tickets on the day.
There you go. It requires breaking the problem down systematically, using both forward calculation and backward reasoning.
That's brilliant. And it really shows how this isn't just number crunching, it's logical problem solving. It's critical thinking that you can apply, well, anywhere, making better decisions in all sorts of situations.
That's the real power of it.
So that brings us toward the end of this deep dive. We've really unpacked the order of operations, PEMDAS. We saw why it's crucial, that whole 20 versus 30 thing. We saw how it works step by step, and we've applied it to riddles, shopping, and even planning a festival.
It reinforces that quote you mentioned earlier from William Paul Thurston. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding.
Exactly. It's about the logic, the structure, the understanding.
And hopefully you feel you've got a stronger grasp of that structure now, that systematic way of thinking, breaking down complexity. That's incredibly valuable, way beyond math class. It helps you tackle complex problems anywhere in life.
It really does. So here's a final thought for you, the listener, to chew on this week. Think about that idea of sequence, of doing things in the right order, the left to right idea or the parentheses first concept. How might those principles, prioritizing certain steps, following a logical flow, apply when you're organizing your to-do list, or trying to understand a complicated recipe, or maybe breaking down a big project at work into smaller, manageable steps? Where else does order of operations thinking show up, even without numbers?
Great question. You'll probably start seeing it everywhere.
Give it some thought. That's all for this deep dive. Thanks for joining us.
We'll catch you next time.